Hey, it is 5:20. Good evening, everybody. Let's get the class started. So for announcements, keep an eye on the assignments. So pre-lab 3 will be due this Thursday, quiz 4 this Friday. If you need any help with that, take a look at the Slack page. There's been a lot of good chatter on the Slack page, different ways of explaining the problems and the labs. Also, my office hours are right after class, so come join me here on Zoom if you have any questions or just want to listen to other people's questions. Also, the TA's office hours are posted on Canvas, and their respective Zoom links are their lab Zoom links. So you can find one Zoom link per TA, so you can join their office hours. So the Slack link, if you go on to the Canvas page, you'll see how to, there's an invite link for Slack. So you can jump on Slack, you click on that, you sign up, and you'll see the conversations going on about the labs and the homework assignments and the quizzes. So take a look at that. So as always, please unmute or chat. I try to see the chat. It disappears on me every once in a while. So, but definitely unmute, ask a question whenever you have a question. And I'm always happy to answer it during class, or if we want to get in deeper, we'll stick around for office hours and talk then. Otherwise, please. Oh, so go ahead.
What about next week's exam?
Yeah, I'm about to talk about that. I'll bring that up in a minute. So let's see. So if I drop off during the class for technical issues, wait around, I'll try to get back as soon as I can. Let's talk about the exam, but first I want to look at the roadmap. So the roadmap of the course is up on the screen. We have covered basic electrical theory, right? This is a volt, this is an amp, this is a watt. And then we looked at analysis of DC circuits, voltage division, current division, Ohm's law, KVL, KCL, node voltage analysis. And this section ends at Thevenin equivalence and maximum power transfer. So we're actually going to be finishing up today maximum power transfer, and that will be the last topic covered on the exam. So what you see today at maximum power transfer, that topic, that's where the exam material ends for exam 1. So speaking of exam 1, it will be next Wednesday, September 23rd. It will cover from the beginning of course all the way up through maximum power transfer and Thevenin included in that. So the exam will be held during this class period because everybody has it free. And I'm going to add a 30-minute grace period to the end of that to get your exam submitted. So the way this will work is you're going to download a PDF file. You're going to work your exam on your own. It's open book, open notes. And so use whatever you want, except for other people. So you have to answer the questions yourself and submit your work. So work alone on that. So you'll work out your exam problems on the exam sheets. If you can't print I recommend printing the exam. If you can't print the exam, then look at the exam on your screen and put your work on a piece of paper of your own and then put a box around your final answer. So then you will submit that to scan it, take photos, submit it to Canvas, and what I'm doing is I'm giving you 30 minutes extra for that. So I don't think you'll need 30 minutes extra. You can use that for extra time to work your problems, but definitely get your exam submitted class period plus 30 minutes. If there's any accommodations, we've already talked about that. So if you have a question about your accommodation, if you have an accommodation, then email me and we'll talk about that. So don't let the open book, open notes part of it be assigned not to study, not to work problems, not to practice. I expect that the exam isn't going to be a huge time pressure if you've studied. If you haven't studied and then have to go figure out how to work the problems real time, time could be a problem. So definitely work some practice problems. On Canvas, there are two types of, I'll say practicing review that you can do. You'll see that there are review problems for exam 1. Those problems are old exam problems. They should give you a feel of what the exam problems will be like. There are also practice problems. That's a different heading on Canvas, and it links you to a web page where I've posted some practice problems, starting out with easy problems, going up through harder problems, and with detailed explanations. So I'd recommend taking a look at both the practice problems and the review problems. Okay, and I will send out an announcement with all this detail on Canvas. I just wanted to give you a heads up. It's 9 days out, and if you have any questions, let me send out the announcement first so you can see all the details, or stop by office hours if you have questions on that. So the current lab work going on right now, right? You started lab 2, I think it is, on, well, no, which was it? Yeah, it was lab 2 last week. And so you should be working lab 2 now. It's due Friday. That lab has to do with voltage division, current division, potentiometers. So they're really practical circuits. And I hope you're making the connection to class, right? So we covered these theoretical topics in class. You should see that they work out pretty well in lab. And then you have a design problem where you actually have to design a variable voltage reference source. And so to meet requirements. If you have any questions about that, again, take a look at the Slack page and also stick around for my office hours and the TA's office hours. But definitely make that connection, you know, what we're doing in class. If you have any questions about voltage division or potentiometers, take a look at those slides or that video, take a look at the Slack page, and it should fit nicely with what we're covering in class. So that's what's coming up. What I'd like to do today is start on figuring out how to calculate a Thévenin equivalent. So last time in class, we talked about the Thévenin equivalent circuit. And this was the last slide that we covered. As a quick review, I said that any linear circuit with resistors and sources, dependent or independent, can be modeled equivalently from the perspective of the outside world, outside of these terminals. It can be modeled with this Thévenin equivalent over on the right. So from the perspective of, get my arrow displaying here, to the right of these terminals, right, of A and B on the right, and to the right of the terminals A and B on the left-hand diagram, you wouldn't be able to tell the difference. Given a set of resistors and a voltmeter and an ammeter, those circuits would behave the same between those terminals. And we talked about some benefits of that. You would have to analyze a complex circuit once, but once you do that, anything connected to those terminals could be analyzed using the Thévenin equivalent. Okay, so what I want to do today is, well, how do you do this? How do you go from this complex circuit to the Thévenin equivalent? You're going to do this in lab. You're going to have a circuit in lab that you're going to solve. It's not this complex, but you're going to see that when you build up that circuit, you calculate the Thévenin equivalent, and the Thévenin equivalent behaves the same way. That'll be the next lab. You'll get that in the future. Okay, how to calculate the Thévenin equivalent. So here's how to do it. I like to say, start with the end in mind, begin with the end in mind, write the answer and fill in the blanks. So here's the answer. Every Thévenin equivalent circuit will look like this. If you're asked, determine the Thévenin equivalent between terminals A and B, or X and Y, or C and D, it will look like this, except you will fill in the value of VT in volts and the value of RT in ohms, and you might have different terminal letters next to the terminals, but the answer is always going to look like that. The first step, or the second step after writing down this kind of prototype template for the Thévenin equivalent, is to determine the Thévenin voltage, VT. So remember, we said VT was equal to VOC. VOC is the open circuit voltage. it is the voltage at the terminals of the circuit between A and B when nothing else is connected. Right? There are connections inside that blue box, but outside of that blue box, you're not going to connect any resistors, no other circuits. You're just going to determine, either measure or calculate the voltage between A and B, and that's called VOC. It's open circuit because you're not connecting anything. So once you determine VOC, that is VT. And we will work an example of this. So now you write your value in volts next to VT up here. You have half the problem solved. The next step is to find the Thévenin resistance, RT. So the Thévenin resistance can be found in one of two ways. The way that always works, but sometimes it's a little harder, is to calculate the short circuit current. And then RT is equal to VOC over ISC. Remember back to that equation that I showed where we said there's this equation for a line that goes from VOC to ISC on that plot. RT is what we defined as, well, negative the slope of that line. We have VOC from the prior step, step 2, and now you need to calculate ISC or measure ISC. You can do that. The way to do that is to apply a short circuit or a 0 ohm resistor between A and B, between those two terminals. And then calculate ISC or measure ISC, right? So you draw out your circuit inside the box, you apply that short, you draw the arrow with ISC going from A to B and calculate it or measure it. So that always works. That method always works. There's a little easier way if you have only independent sources inside that blue box. So circles, right? No diamonds. Remember, circles, either current sources or voltage sources, are all independent. If you have any diamonds, dependent sources. Number 2 does not work. So this only works for independent sources. But if you have a circuit with only independent sources, then what you do is you set all of the sources values, voltages and currents, to 0 volts, 0 amps. And then you calculate the equivalent resistance between the terminals. So I'll show you an example of this in a minute. Okay, so that's still a little cryptic. You still have sources in this circuit. How do you deal with that? Well, let's talk about that. So let's suppose you've determined your circuit has only independent sources. So you want to use method number 2 here. So here's what it means to set sources to 0. If you have a voltage source, independent, then you set its value to 0. It might have been 12 volts or negative 5 volts before. You set it to 0. And so what that really means is you can replace that 0 volt source with a short, right? Both of these, left side of the equals and right side of the equals, both of these enforce 0 volts between those two terminals inside your circuit. And for a current source, when you set it to 0 amps, right, inside your circuit, because you're using method number 2 that I just showed, you replace that current source with an open, because that's another way to enforce, to cause a 0 amp current to flow between those terminals. Okay, so to calculate the Thévenin resistance, when all sources in the circuit are independent, you replace all of the independent voltage sources with shorts. You replace all of the independent current sources with opens. And then you calculate the equivalent resistance between the terminals. And then the Thévenin resistance is that value. Okay, so I am going to walk you through an example now. We're going to do this. Let me go back one slide. We're going to find VT, we're going to find RT, and we're going to find RT both ways as a demonstration. Okay, so let's move to the whiteboard. So here is a straightforward circuit. And what we want to do is find the Thévenin equivalent of the circuit. So the question would say, between terminals A and B, find the Thévenin equivalent. Okay, so step one that I showed was, let's create the answer. Let's draw the answer. So that's the answer, right? VT and RT, and between terminals A and B. And now we have to fill in those values, right? What is VT, what is RT? Okay, the next step is to find VOC. So we know that VT equals VOC. Okay, so that's what we have to find. So let's go up to the circuit. And what we want to find is, without connecting anything to the right of these terminals, this value. The open circuit voltage between those two terminals, between which we're trying to find the Thévenin equivalent. Okay. A couple ways I see to do this. One is voltage division. We actually have a voltage across 3 series resistors. So these resistors are in series because the same current flows through them, right? The current that flows through the 10 ohm resistor flows through the next 10 ohm resistor, flows through the 40 ohm resistor, and back to the source. If you had connected a resistor, let's say externally to A and B, well, then the 40 ohm resistor would no longer be in series with those 10 ohm resistors, but we haven't connected anything. So at this point, for this circuit, 10, 10, and 40 are in series. So I can use voltage division to solve for the voltage across the 40 ohm resistor. That's what VOC is. It's the voltage from this top node to this bottom node across the 40 ohm resistor. So I can say that VOC equals, let's see, the pattern is this. It's the voltage across the series set of resistors times, on the top of this fraction, is the resistance across which you're trying to find the voltage, and on the bottom is the sum of all the series resistors. Okay, and so that was voltage division. I'll write V div here. And so what you would find is VOC equals 8 volts, and that equals VT. So now over here on the left-hand side, I've solved for half of my Thévenin equivalent. So this is 8 volts. So I mentioned there are 2 ways. You could also maybe combine the 10 ohm, and the 40 ohm resistor into 60 ohms, figure out the current flowing through the circuit, multiply that current by 40 ohms, Ohm's law, and get VOC. So there's multiple ways to solve for this. Okay, next let's solve for RT. So I notice in the circuit that I have only an independent source. There's a circle, no diamonds. Okay, I could have multiple independent sources, but I have no diamonds, only circles. So that lets me use, I would say, the easier approach, approach number 2 on the slide that I just showed. We're going to zero the source and then calculate the equivalent resistance between the 2 terminals. Okay, so what I do is I'm going to draw the circuit again, but I'm going to replace 12 volts with 0 volts. And as I showed on the last slide I showed, I can replace that source with a short, because this, a short, is 0 volts. And then I can draw the rest of the circuit. Okay, and then what I'm going to do is I'm going to find the resistance, the equivalent resistance between A and B. Okay. Let me draw something in here. Let me show you what I'm doing when I'm finding this equivalent resistance. Remember that I'm really, you don't have to draw this, but what I'm really doing is I'm applying a voltage, and right, that would be the voltage, and I'm figuring out what the current would be, and then combining in series and parallel, or doing whatever I need to do to find the resistance between those terminals. I draw this because I want to point out that, well, the 10 ohm and the 10 ohm resistor are in series. I can combine these together, right? And this is 20 ohms. And then the 20 ohm resistor equivalently connects between the same two nodes as the 40 ohm resistor, right? So this 20 ohm resistor and the 40 ohm resistor are in parallel. They connect to the same two nodes. So what I would say is that REQ, I'm going to say RT equals, REQ in this case, equals these two 10 ohm resistors in series in parallel with, so two lines, that means parallel, shorthand for that computation of parallel resistors, in parallel with 40. Okay, so 20 in parallel with 40. Now what's weird, what bothers some folks is that, wait a minute, up here I said that these resistors were in series, and I used voltage division because they were in series. Well, yes, because I had a 12 volt source, the current flowing was from that source through the 10 ohm resistors down to 40. Down here, now I'm saying, wait, the two 10 ohm resistors, 20 ohm, is in parallel with the 40 ohm. Well, that's because I'm looking at the circuit from a different perspective. Now, I want to find the equivalent resistance between A and B. So it's as if I'm applying a source to get a voltage across those terminals, determining the current, and when that current I flows, now that current splits between 40 and these two 10 resistors, two 10 ohm resistors. They are no longer in series, right? This up top is a different circuit than this circuit at the bottom, okay? But either way, if you run, well, not either way, but if you get that, if you buy that the equivalent resistance is 20 in parallel with 40, then you will see that the equivalent resistance and the Thévenin resistance is 13.3 ohms. And so now I write 13.3 up here. And that's the answer, right? That's the Thévenin equivalent of this circuit. So if I put this circuit in a box and I expose the terminals A and B, and I put this circuit in a box and I expose terminals A and B, you would not be able to tell the difference just by having a voltmeter, an ammeter, some resistors. The V versus I characteristic would be exactly the same. You're going to see that in lab. Okay.
Professor?
Yes.
Can you explain that again, why we're considering the resistors to be in parallel when finding RT?
Right. Okay. So when you find an equivalent resistance, what you're doing, and when we derived, if you go back to when we derived series and parallel combinations of resistors, what I did is I applied a voltage and I calculated a current, and I got REQ equals V over I. Okay, so that's really what you're doing when you are calculating equivalent resistance. Now, what we say is for the Thévenin equivalent, that's what you're doing. You're calculating the Thévenin equivalence. You're calculating the equivalent resistance between A and B. So to do that, what you would be doing is applying voltage, measuring current, and calculating V over I. Well, this current I, it goes this way, it splits, it goes down this way. So the 40 ohm resistor and these two 10 ohm resistors do not have the same currents going through them. They have different current. Does that make sense that if I apply a voltage source here, that one current goes down this way, another current goes this way, and they are not the same? They both combine and they come back this way, right? But They are not the same. So does that explain why they are not in series here?
So are you you're saying that we're like acting as if there is now like a resistor between A and B that we have to solve for, or?
Well, I'm saying we're acting as though we're applying a voltage to A and B to try to figure out, looking into this circuit right in that direction, if I were to apply a voltage and I calculated the current, what would the equivalent resistance be?
So what is that voltage then?
You can make it any voltage you want. You can make it 5 volts, 10 volts, 100 volts. It doesn't matter, because whatever V you get, whatever V you use divided by whatever I you calculate will be a constant value.
So if I'm understanding this correctly, we have a voltage between A and B, like this hypothetical voltage V out, and as such, that means we sort of want to have this hypothetical imaginary circuit element with a voltage source and current. And then depending on the direction of that imaginary current, we use that to determine that since this imaginary current is flowing to the left, that when it reaches that intersection, it will split, and thus the action of splitting, as we have established, will make it parallel.
That's right. And I'm going to say this in general: when you're calculating an equivalent resistance, right, you have some kind of resistor network, you don't know what's in there. What you're going to do is, first you're going to say that this behaves like Ohm's law, right? That's a requirement. This circuit has to behave like Ohm's law. And what does that mean? That means if you were to apply a voltage and you were to measure the current, right, I, that this would be equivalent to a resistor whose value, REQ, equals V over I. Right? So if I replace this maybe complex resistor circuit with a single resistor whose value is V over I determined up here, that's what equivalent resistance means.
Right.
So we're doing the same thing down here. I'm saying, okay, the Thévenin equivalent tells me this down at the bottom. This is the Thévenin part down at the lower left. RT equals REQ. Let's just accept that for now. So we have to find REQ. To find REQ, you do basically what I'm doing in the upper right. You apply a voltage and you measure the current, and then you get this answer. What we said was, well, for series resistors and parallel resistors, well, we don't have to do all these calculations. Series resistors add in series, and parallel resistors combine as they do, right, in parallel. So that's what I'm showing here. You don't really have to draw any of this red part of the circuit, but you do have to recognize that if I were to connect resistors like this, if I connect a 40 ohm resistor and a 10 ohm resistor, and I expose two wires, and then I take an ohm meter and I apply an ohm meter between A and B, what it's doing is actually applying a voltage and measuring current and doing that calculation for you. That's what an ohm meter does. It applies a voltage, measures the current, and shows you the result of that division. But what you would see is that because you're applying a voltage between A and B, and you have a current flowing into A and out of B, that current would split. So the same current wouldn't go through the 40 ohm resistor and the two 10 ohm resistors. So they're not in series, but you can say that they connect to the same two nodes, as drawn in this circuit right here.
So we can justify the existence of this sort of imaginary current by basically saying that we are essentially imagining a resistance between A and B, and as such that would, my brain can't make the last connection.
Okay, so
it's basically as if we were measuring it with an ohm meter.
it is.
Okay.
And that would establish a resistance and thus a current.
So I'm going to take an ohm meter and I'm going to measure this circuit, right, without the red. Forget the red there. I'm going to measure this circuit, and then I'm going to, if I came over here and I put a 13.3 ohm resistor, of course I'd measure 13.3 ohms in both of these cases, between both of those pairs of terminals.
Okay, and that's because in applying a voltage, you would make those resistors be in parallel then. So that's why it's series in the top and then parallel at the bottom.
Yeah, that's
Okay.
right. Because up here now, this really is a different circuit. Here I have a voltage source on the right. Here I have a voltage source on the left. They're two different circuits, really.
Okay, thank you.
Sure.
And is that how thermocouples work?
So thermocouple. So we're going to get to that toward the end of the semester if we have time. Thermocouples actually are voltage sources. So a thermocouple creates a very small voltage, and a thermistor, which is a type of heat measuring device, temperature measuring device, actually is a variable resistance whose resistance changes with temperature.
Gotcha.
So,
that answers my question. Thank you.
Yeah, sure. Okay. No, good questions. Okay.
Professor?
Go ahead. Yeah.
Sorry, just to quickly clarify. So, that red node with the red voltage source there, that's all essentially imaginary, right? That's like just there for the sake of finding REQ.
That's right.
Okay.
That's right. If you just recognize that between A and B, that the 40 ohm resistor and the combination of the two 10s in series are in parallel, then you wouldn't have to draw any of this.
Okay, thank you.
Mm-hmm. Okay, so this is probably the easier way. We had a lot of discussion, but you could see once you recognize how these resistors would combine, that you know, this could be a pretty quick calculation. You do this calculation, you get 13.3 ohms. Let's suppose, I don't know, you have a dependent source, or you just wanted to work to find the value of RT a different way. So let's find RT a different way by finding the short circuit current. So let me draw this circuit again, sort of. I'm going to change it a little bit. So that's the same circuit. But what I'm going to do now is I'm going to draw a short. And through that short, if you were to build this or, you know, analyze this, we would call this current through the short a short circuit current. So, and then we would know that RT equals VOC over ISC. So we have VOC, it's 8 volts. We need to calculate ISC. Let's talk about how to do this. So now it's an analysis problem. It's not a Thévenin-Equivalent problem anymore. It's just figuring out what this current would be. This problem is a little weird. Let me walk you through, instead of just throwing out what the solution is, let me make some observations here. The voltage, so let me figure out the voltage across that 40 ohm resistor. See what's going on here. Remember, if I take, let me start out here. If I take two probes of my voltmeter and I touch them to the same node, you would see 0 volts. In fact, I encourage you to try this during lab. Take your voltmeter from your AD2 and connect that voltmeter to a node that maybe has, I don't know, 5 volts, even a power supply node, and take the other terminal of the voltmeter and connect it to the same node. You'll see 0 volts, maybe a couple millivolts, but about 0 volts. So if I touch my leads of a voltmeter to the same node, I will always read 0 volts. Okay, well, this node, right, if I touch where I'm showing now, I would see 0 volts, I would see 0 volts, I would see 0 volts because I'm still on the same node. Remember, the node is the entire connection between circuit elements. And so now the voltage across, if we were to measure this, that 40 ohm resistor is actually 0 volts. The top and the bottom of that 40 ohm resistor are connected to the same node, right? So if you measure voltage at the same node between a node and itself, you would see 0 volts. by Ohm's law, right, the current is voltage over resistance. So I would see 0 amps, if I can fit that there. That says 0 amps right there. So I have 0 amps through that 40 ohm resistor. Okay, so what does that mean? That means that, well, I know I have ISC coming this way, right? I have 0 going down through that 40 ohm resistor. So that means that this current is ISC, right? ISC goes this way through the 10 ohm resistors, 0 goes down through that 40 ohm resistor, and ISC goes down this way. So it's just an observation I can use to try to figure out, well, how to figure out that short circuit current. What I would see also is, let's see, Ohm's law would tell me the voltage across that 10 ohm resistor is I times R, or 10 times ISC, right? The voltage across this 10 ohm resistor is I times R times I, 10 ISC. And now I could write a KVL equation. Why do I say that? Because I think if I write a loop around the outside, I have only ISC as an unknown, right? Minus 12 plus 10 ISC plus 10 ISC. Let's see, plus 10, right? Back to the starting point equals 0. Okay, so what I get is ISC equals 12 over 20 equals 0.6 amps. Okay, well, now I have what I need to find RT, because then RT equals VOC 8, right, 8 over ISC 0.6. And if you run that calculation, you would see that's 13.3 ohms. So we get the same result, right? We get, either way, we get the same result for RT. I would claim this lower left approach is a little easier. But remember, you can only take this lower left approach if you have independent sources. If you have a diamond in there, a dependent source, then this does not work. You have to use the short circuit current approach.
Question.
Yes.
Can you explain again why there's 0 volts across the 40 ohm resistor? Is it just because like current's going to go path of least resistance, and since there's no resistance at all?
Right. Well, let's see. So let me ask this. If I does it make sense that there is no voltage between a node and itself? In other words, if I have a wire, let's say with 2 resistors connected, right? And I measure the voltage between that point and that point, right? Does it make sense that you would see 0 volts between those 2 points?
Yeah.
Okay, so let's make this that point and that point in the upper right, 0 volts, that point and that point, right? 0 volts, because it's all in the same node. So I can keep tracing this around as long as I touch my voltmeter to the same node, right? Both terminals to the same node, then I'm going to read 0 volts. And so, in fact, this whole connection here, I'm going to circle the whole thing. This is all one node, right? That's all one wire, and there's always 0 volts between a wire and itself. And both sides of this 40 ohm resistor are connected to the same wire.
Okay, that makes sense.
Okay, good.
Thank you.
Professor?
Yes.
They said the previous method we did is when there's only independent sources in the circuit, correct?
That's right.
So for this one, are you essentially like changing the circuit when you're adding the short circuit on the end?
Yeah. When you analyze this circuit, it's different than analyzing the circuit on the left. It is so the circuit to the left of the terminals is exactly the same, but I'm changing the load that I'm applying to it. Remember that, let me go back to this. We drew a plot when we started talking about Thévenin-Equivalents, where I said this is the voltage across the load, right? So the load, let me go up on the right and add a load here. Let me get rid of this VOC. So if I come up to on this right side and I add a load, if you change this load resistance value and you did a plot of the voltage across the load versus the current through the load for different values of RL, you would find a straight line on that graph. And where the current is 0, right? This is 0 amps down here. Where the current is 0, that is the open circuit voltage. So this would be VOC. And where the voltage is 0, this is in the upper right, this is the voltage 0 case, and when you apply a short, that's ISC. And then you're finding the slope of that line to figure out RT.
Okay.
So for each one of these cases, right, you can put a resistor that causes that to happen, or causes that to happen, or causes that to happen. You're actually applying different load values, different resistor values to the output, and you're trying to figure out what the slope of that line is and what this intercept point is. That's the whole point of the Thévenin-Equivalent.
Okay, I see. All right, thank you.
So yeah, so everything inside the box stays the same, well, except for this case down here. This is a special case where you're turning off the source and measuring the resistance, but yeah.
But that's,
So if,
sorry, but that's just part of the method when you have only independent sources, correct? Or was that like, is this like a special kind of circuit?
no, this is that's just the method. It's just the method. What you're really trying to do is you're trying to say, if this circuit were in a box, right? So that green box, I cover that up, and then I take this Thévenin-Equivalent and I put it in a box. What value of RT and VT should I use such that outside both of those green boxes, you couldn't tell the difference? And this is the method. These are the methods in order to calculate VT and RT.
Okay, thank you.
Okay, sure. So you'll see examples. There's actually those practice problems that I mentioned linked to Canvas. You'll see those. You'll see some examples there. Okay, so what I want to do now is I'd like to talk about, well, let's suppose you have a source. Now, by source here, I don't mean an ideal source. I'll explain that in a second. But suppose you have like a battery or something like a sensor, like a temperature sensor, a weight sensor, or maybe you have, I don't know, an antenna. That's a realistic source. And realistic sources look like this. They look like a Thévenin-Equivalent. I mentioned that on the back of your stereo, it might say something like 8 ohms next to a speaker output. That 8 ohms is actually the Thevenin resistance of that output. There's a big complex circuit in there with an amplifier, transistors, lots of other stuff, capacitors. But at audio frequencies, you could model that speaker output, that amplifier, with the Thévenin-Equivalent. We're going to call that a source. It's not an ideal source. It's just a source. On the right side, what you connect is the load. That would be the speaker in the amplifier case. So again, audio amplifier to a speaker, a sensor to a data acquisition device, right? Sensor would be the source, data acquisition device would be a load. An electric guitar output would be a source, and then the amplifier input would be a load, and at radio frequencies, an antenna to a receiver. So the goal is to do this. The goal is to figure out if I have a source like your stereo, and I want to figure out what load resistance do I need to connect in order to get maximum power transfer. What value in ohms? We want to figure out how to get the most power transferred from a given source to a load. Okay, why is that important? If this is an antenna, you want the best audio quality. So you want the highest signal power compared to the noise power. The more signal you have, the more signal power you have, the cleaner your audio is going to sound at your receiver. So let's work on this. Let's figure out first, what is the power delivered to the load? It's going to be the load current times the load voltage, just like we talked about in the beginning of class. Ohm's law says that the current is going to be equal to the voltage across those series resistors divided by that total series resistance. Let's figure out the voltage now. The voltage VL can be calculated using voltage division. You know, VL is in or RL is in series with RT. You know VT. You can multiply these together and get the PL. So this IL equation times that VL equation is what you see at the bottom here. That's the power provided, given to, delivered to the load. That's what that load resistor is absorbing. Let's suppose you want to maximize that so you have the best audio quality out of your radio receiver. Now here's the topic of maximum power transfer. You want to transfer as much power as possible to that load resistor. So here's that schematic again. Let's just take a look at the extremes, right? The extremes, remember, we're trying to adjust RL in order to get maximum power to RL. If we look at extremes such as, well, let's build a table. For a given RL value, let's calculate PL. If I have the extreme of 0 ohms for RL, I get 0 volts across that load times whatever current is 0 watts. If I go to the other extreme, infinity, right, an open circuit, then I get 0 current. So no matter what voltage I have, 0 times whatever is 0 watts. So the maximum power transfer does not happen at 0 or infinity. It's somewhere in between. And so we got to figure that out. The calculus approach would say, well, we have the equation for power versus load resistance. So let's take the derivative and solve for RL, and that will give you the answer. What I'm going to show you, and what you would see in lab, what you will see in lab is this. Let's take an example circuit. So here's an example circuit. I have a 10-volt source with a 100 ohm resistor. That's my Thevenin equivalent. That's my realistic source on the left. On the right, I have R sub L. That is the load resistance. I want to figure out what value in ohms, 10 ohms, 300 ohms, what value does that have to be to get maximum power transfer from the left side of the terminals to the right side of the terminals. So I create a plot. I can plot that equation. I can calculate current and voltage or measure it and for different values of RL. And I would see this. So this is a MATLAB plot. Along the x-axis, I have the resistance, that load resistance value in ohms. On the left side, that's the power that's actually delivered to that load resistor. It's how hot it gets. If it's a speaker, it's the audio power getting to that speaker. If it's a radio receiver, it's the power being delivered to that receiver from the antenna. But you can see there's clearly a trend, there's clearly a maximum here, and then it falls down. It's in line with that very short table that I showed on the prior slide. At a load resistance of 0 ohms, I have 0 watts. And then as you go out to infinity, you'll see that the power falls. Okay, but this peak, what's important is we want maximum power transfer. That peak happens right at 100 ohms. Experimentally or through calculations, you'd see for this source, you have maximum power transfer when RL is 100 ohms. So max power transfer occurs at RL equals 100 ohms or RT equals RL, RL equals RT. So the big takeaway is this. For maximum power transfer from a realistic source, from a Thevenin equivalent to a load, you set the load resistance equal to the Thevenin resistance. Okay, that's it. That's the conclusion out of this. So once you have a circuit and you can calculate its Thevenin equivalent, you know how to get maximum power transfer from that circuit to some load. So if you have a stereo that says 8 ohms at the speaker jack at the output, that means use a speaker that looks like an 8 ohm resistor. If it says 16 ohms, use a speaker that looks like a 16 ohm resistor. That will give you maximum power transfer from the amplifier to the speaker. Okay. So, so this covers the material on Thevenin equivalence and maximum power transfer. It also ends the material that is applicable to exam 1. After this topic, we're going into capacitors and inductors, though those will not be part of exam 1. So right here is the break point. You'll see that your homework that's due Wednesday actually ends here at maximum power transfer. So you'll be able to work your homework problems that apply to exam 1 before you actually have to take exam 1. Right? So what I will do is end class right here, and if you have any questions, then stick around for office hours. Remember, the exam is next week. Check out the assignments and the review problems on Canvas, and definitely see the Slack workspace. I see lots of people answering questions about the lab, and I think that will increase as the labs get more complex. So you got lots of people participating there. So thanks for joining class. I hope it's working out well. If it's not, please let me know. I will drop on mute for a couple minutes. And if you want to stick around for office hours. If not, I'll see you next time.